Okay, so welcome everybody. This is the third non-public lecture. I was just amused by the fact that it's the same public, so I'm not sure how this differs. Today we're going to cover the following topic: the physics of neutron star mergers. And as I've done yesterday, I'm suggesting some references. There is a review by Luca Baiotti and myself, and Reports of Progress of Physics. I think it has a lot of interesting information in it. There is another one by Vasilis Pascalidis, Classical and Quantum Gravity, and some of the aspects I'll cover here are also, again, contained in my book. So, what we're talking about here is two-body problem. I know that you have something else in mind when you think about two-body problem, but here we mean a problem where we have two objects which have a given mass, m1, m2, which are interacting only gravitationally. And in Newtonian gravity, this problem is extremely simple to solve. In fact, this is the solution to the problem. Okay? You are just asking for a balance between a gravitational force and a centrifugal force. An important aspect, I think this is something that I'm sure others have looked at and discussed, in particular Scott, is that in this context, the orbits are closed, and it's therefore very easy to come up with stationary solutions of this type. However, in Einstein's gravity, this is no longer the case. Okay? There are no analytic solutions. The orbits are never closed, and this is because the system loses energy and angular momentum via gravitational waves. So, if you think about it then from very first principle, in an abstract manner if you want, you can think that this is a two-body problem where you have two objects at the beginning, two black holes or two neutron stars. You assign some momenta, linear momenta, and then you study what is the evolution of these objects. And in the case of black holes, we know what happens. You take two black holes and you obtain at the end a black hole plus gravitational waves. You can think this is a scattering problem. Okay? In the case of black holes, this is something we already have observed. Okay, so this is 150914, first detection of binary black holes. So this is not just a fantasy, this is reality. We do know that this process does take place in nature. In the case of neutron star, the situation is similar but different. You also start with two objects at the beginning, out of which you assign initial data, and at the end of the day, you also end up with a black hole plus gravitational wave. So you may think that the initial and final states are the same. However, there are important differences. The first one is that as they merge, the two neutron stars not necessarily produce a black hole. Actually, in the large majority of the cases, will not produce a black hole, at least initially. What they produce is what is called a hypermassive neutron star. That is, a neutron star which has a mass way too large than it can sustain through uniform rotation, and so is differentially rotating. But this is a metastable object. It is not in equilibrium. It is there just because of differential rotation, and after a while it will collapse to a black hole, and some of the matter of this star will produce a torus, simply because they are on stable orbits. But the torus will accrete eventually onto a black hole, and that's why eventually you end up with a black hole plus gravitational waves. Now, these two distinguishing features are very important in the case of binary neutron stars, and this is where I put question marks, because this is where all the difficulties are, but also where all the interesting physics is, and astrophysics. In particular, and I'll explain this better, if we understand what happens during this stage, there is a very good opportunity for us to understand what is the equational state of neutron stars. If we understand what happens during this stage, and I'll explain this also, chances are that we can understand what produces gamma ray bursts. What we know now is that gamma ray bursts, short gamma ray bursts, are associated with binary neutron star mergers. But we don't know what produces a gamma ray burst. Okay? The idea is that there is some jet, ultra-relativistic jet, that is produced, but we have no idea how this is actually produced from first principles. and what are the physical mechanisms that are actually powering this process. Another reason why both of these stages are interesting is that there is some matter which is ejected in this process, okay? As you know, these objects are colliding at a fraction of the speed of light, and you can imagine if you take two very compact objects and you smash them at a fraction of the speed of light, you're going to have some matter, in fact, a little matter of the order of a few percent of a solar mass, which is unbound. It has very large energies and therefore can escape the gravitational field. This is what we call ejected matter, and this matter is hot and dense and can go nucleosynthesis. And in particular, it can produce lead to the nucleosynthesis of heavy elements like gold and platinum. So all of those elements that we really like a lot are actually produced in neutron star mergers. We now believe that a large majority of gold in the universe is produced by mergers of neutron stars. It's not clear they produce coins, but they certainly produce gold. Okay, yes?
Is there a supernova
Between 2 and 3? What do you mean, 2 and 3?
From going to the neutron star to the black hole, there should be some kind of...
No, so the supernova is in this direction. This is the supernova has led to the neutron star. So a supernova explosion produced a neutron star. Okay?
After that, from that hypermassive neutron star to the black hole, how...
I'll show you. It's a dynamical process. Okay? Okay, so these are the equations we need to solve. I have explained to you the mathematics behind how to solve these equations. I can ask questions about to see if you remember everything. Probably not. Okay? But you have to imagine that there is a whole different dimension on how to solve those equations from a numerical point of view. Okay? So this will require far more than a school to explain all the technical aspects of going from the mathematical equations we looked at yesterday into equations that you can solve on a computer. There is a whole bulk of literature on how to do this, and we don't have time. But again, if you're interested, there are books where you can find this. So these are the equations that we want to solve, and you invest 10 years of your life and of the lives of very good students, and you end up producing codes that are able to do something like this. So this is a simulation that shows what happens to a binary neutron star system. The mass is twice 1.35 solar masses. This is a realistic equational state. It's called LS220. It's a hot equational state. And what I'm showing here is the density, the rest mass density. So the two stars orbit around each other. They are treated as perfect fluid self-gravitating objects. As they get closer to each other, they distort themselves, they tidally distort themselves, and then they merge. This is when they produce the hypermassive neutron star. You see, it's an object which is very highly rotating, very rapidly rotating, is differentially rotating, and is losing a lot of angular momentum through gravitational waves. And because of this, it's spinning and losing angular momentum. At one point, it will no longer have enough angular momentum and will collapse to a black hole. And this is a configuration I was mentioning. So you have a black hole surrounded by a torus. And the transition from hypermassive to black hole is dynamical, as I was saying. And the time scale for this to happen is very uncertain. It depends a lot on the equational state and on the mass. It can be a few milliseconds up to 1 second. Okay? Okay, so the density of this torus may look very, very tenuous. Actually, it's very large. It's 10 to the 8, 10 to the 9 gram per cubic centimeter. So this is really dense matter. Okay? And it's because of this that, neutrinos can be produced by this object. The picture I've just shown you, merger, hypermassive neutron star, black hole plus torus. This is extremely robust. Okay, I can make a very complex picture where I put a lot of microphysics and other effects, but this basic feature, the merger, the hypermassive neutron star and black hole plus torus, is very robust. So no matter if there is something you have to remember out of this lecture, is that when you have two neutron stars, they first produce an hypermassive neutron star and then a black hole plus torus. What are the possible changes or the degrees of freedom in this picture? One is the total mass of the system, and which is responsible for prompt versus delayed collapse. To explain this better, I've made this cartoon where I have time on this axis, and I have the mass of the system, m, normalized to the maximum mass that a star can support. Say this could be around 2 solar masses, and so this is the typical scenario that one thinks to encounter. For millions or tens of millions of years after the 2 stars have been produced, they will orbit around each other. They will produce gravitational waves at very low amplitude, at very low frequency. Then, in a time scale that, as I said, is between 1 millisecond and a second, they produce an hypermassive neutron star. This collapses to a black hole, and this black hole this torus survives for about 1 to 100 seconds, and then you produce a black hole in vacuum. Okay? Now, suppose you change the mass of the system. You make it larger. Okay? Just consider the 2 stars to have each 2 solar masses. Then what happens is that, okay, they will orbit just the same, and you miss this part. Immediately after the merger, there is a black hole that is produced, and of course then the torus will be accreted, and you end up with a black hole in vacuum. Or, this is the other possibility, you have very low mass stars. Again, they orbit, they produce a hypermassive neutron star, and this object then becomes a uniformly rotating star, or a supramassive star. This could lead to a protomagnetar, for those of you who know what that is. And this object then has 2 possibilities. Either will produce a star, a non-rotating star, which is in equilibrium, if the 2 initial stars are very small and the maximum mass is very large, or they will produce a black hole. And in this case, it may even produce a fast radio burst. Okay, so this is one of the possible changes in the scenario if you change the mass of the system. There are other differences, and one of them is the mass asymmetry. Okay, in the first simulation I've shown you, and that simulation was not computer graphics, that was the solution of those equations that we have seen yesterday. This will lead, in that case, the 2 masses were the same, but in general, you would expect that the 2 masses are slightly different, maybe 90% the same, but there might be a 10% difference in mass. What happens in this case is shown with this other simulation. So here you have a system which has a total mass of 3.37 and a mass ratio of 0.8. This means that one of them is 20% heavier than the other. Which one is the heavy star, the left or the right one? Well, equally. Should we flip a coin? It's clearly this one, okay? It's denser, and you can see there is a higher color here, and it's also smaller. This is typical. As you increase the mass, the radius becomes smaller. So keep an eye on this little star, because it's the one that has the strongest gravitational field. And what it will do is it will break apart the other star. It will accrete a lot of matter, and as a result of this, will break itself apart, distributing a lot of matter around. These are called dynamical ejecta because they are ejected through dynamical tidal forces, and they represent a very important component of the ejected mass. This mass that you see here in this spiral arm, well, most of it will fall back, but a little part of it will not, and will actually go on to produce the matter that gives life to nucleosynthesis. Now, what you can learn is that in general, the tori are more massive in this case, they are more extended, and they are having a quasi-Keplerian rotation. This means that these configurations are stable for long periods of time. I mean, long means seconds or hundreds of seconds. And this is important to have a lot of matter in the torus, because the torus is where you have binding energy. So you can use this binding energy later on to fuel maybe a short gamma ray burst. Okay, let's go back to this picture. So we've seen total mass asymmetries. The equation of state is also very important and provides a different behavior. Magnetic fields are also very important, and they are important both for the equilibrium and for the electromagnetic emission. And then there are radiative losses. As you can imagine, this is very hot material, very dense and hot, so neutrinos are going to be produced very abundantly, and they will take away energy and momentum. And besides, they are important for the nucleosynthesis because they change through the interactions, weak interaction, they change the composition of the matter. So all of these are things that we can, in principle, incorporate in our codes. In fact, our codes can describe all of these different aspects. Most of the time, we don't put everything together because we like to understand one aspect at a time. And in particular, what I will discuss now is the impact of the equation of state. So this is a binary black hole gravitational waveform. Okay, this was made by myself in 2006. I calculated this. At that time, we could do very short waveforms, but this waveform, besides being, personally attached, has all the features of this that are important. I don't know if Scott has already discussed a little bit how to read a gravitational waveform, but this is what I will do with you. So there is a part which is called a chirp signal. Why is it called a chirp signal? Does anyone know? High, what is high? What gets high? Not only the frequency. So the frequency gets high, but also the amplitude. Okay? And why is it called chirp? Because it sounds like a bird. That's what a bird does. Okay? It goes up in frequency and amplitude. And then there is a ring down. Okay? So this is an exponentially decaying part of the signal. Okay, if you want to look at what a binary neutron star waveform looks like, it's like so. So it has, again, a chirp signal, and you have to imagine this waveform goes and in this direction for about 10 million years. But we're interested just in the last 5 milliseconds. Then there is a portion which is a transient over here. There is a part which is the one produced by the hypermassive neutron star, okay, over here. And then the new hypermassive neutron star collapses and you produces a ring down, okay? So if you want to compare black holes versus neutron stars, essentially it's all this piece in between, okay? In the case of black holes, it's just chirp and ring down because there is nothing that can happen in between. In the case of neutron star, there is all of this signal that is there. You can think of looking at this signal not only in time, so this is a gravitational wave amplitude in one polarization versus time, but you can see the same signal in frequency. And this is what I guess, Nerji was mentioning yesterday, how to see a signal. Just let me go back through it again. You have a power spectral density of the instrument, so this is these curves over here. And then you have frequency over here. And any gravitational waveform will represent a line, a track in this space, okay? So you start up here, low frequency, high spectral density, and then you move in this direction towards higher frequency as the spiral proceeds, and then the frequency go up. Now, at low frequency, you have a large spectral density because of what? I just said that the signal here is extremely weak. So why is it that we have so much power at low frequency? The power at a given frequency depends on the amount of time you spend at that frequency. So the star spends millions of years at this frequency, and so you can pump, at the end of the day, a lot of energy. As you go into higher frequencies, you have less and less power, because at a given frequency, you'll spend less and less time. Okay, now let's make a Gedanken experiment. Let's think that we have two black holes of 1.4 solar masses. We don't think they exist in nature. We think black holes are of order 10 or more solar masses. But if they existed, the track in this diagram would be the black line. So they would have almost a straight line, a power law, because it's a log-log plot. And then they would be, here there would be a little bump. This is really the chirping signal. You are emitting much more energy here. And then there is a cutoff, an exponential cutoff, because of the ring down. Okay? Now, let's do the same experiment with binary neutron stars, 1.4 solar masses. These are the blue lines. So at low frequencies or large separations, then black holes and neutron stars look just the same. They produce exactly the same. They move just like point particles. But then as the frequency increases, because the neutron stars are made of matter and they have a finite size and they can be tidally distorted, you have the tidal effects will make the two tracks different. In the time domain, you have to imagine that the waveform will start dephasing one from the other. Then there is the merger, and you can see the merger happens at about 2 kilohertz, while in the case of black holes happen at 6 kilohertz. So neutron stars tend to merge earlier because they are bigger. Then there is this massive signal over here where you see all of these wiggles, and then there is a cutoff and a ring down again. So what I would like to do today is not only explain how to distinguish the black and the blue, but also how to distinguish the two blue lines. The two blue lines are two different equations of state, and so in principle we can learn about the equation of state by just looking more in detail at this messy signal. So this is a kind of simulations that we can do nowadays with our codes, and they allow us to make very colorful plots. To make this plot, we have burned computing time for about 1 year on a supercomputer. And I can explain all the content of this plot in about 60 seconds. So, different colors are different equations of state, and different columns are different masses. Okay? So you have APR, MF2, and so on. In general, this is a soft equation of state, this is a stiff equation of state. What you can see is that a soft equation of state has a post-merger signal, so after zero, that is much smaller than the pre-merger signal, the one during the spiral. This is the opposite in the case of stiff equation of state, where instead you have that the post-merger signal is comparable. This is easy to understand. A soft equation of state means you can compress matter very much, the object is very compact, and so doesn't have large perturbations, large asymmetries, and so it doesn't produce a lot of gravitational waves. Vice versa, a stiff equation of state, you cannot compress it much, and so you have a big object which is rotating very rapidly, is emitting a lot of gravitational waves. Another thing you can notice is that the frequency of the gravitational wave signal after the merger for a soft equation of state is higher than for the stiff. You can tell that here you cannot distinguish the different peaks. Here you can still see the different peaks. Okay, so this is high frequency, this is low frequency. Another thing you can notice is that this object, for a sufficiently high mass, this object after 25 milliseconds collapses to a black hole. You can't quite see, but there is a ring down there. This object instead can stay alive for much, much longer. That's because it's not losing a lot of energy, and therefore is not forced to produce a black hole. Okay, so that was roughly a bit more than 60 seconds, but that's really all you need to know about this. Okay, at least from a big picture. Now, these very same objects can be seen in the frequency domain. And so now I'm just concentrating in the messy part of the signal, the one that I was showing before. And I don't ask you to look into the details of this. I will explain this better. But what I want you to understand, I appreciate that these are lines. If you've taken a course in astronomy and stellar atmosphere, and you've learned that you can tell what a star is made of, at least the surface layers, by just looking at the light it emits. And what you do is you look at absorption and emission lines. It is exactly the same. What you are looking at here are lines, they are spectral lines, and so this is gravitational wave spectroscopy. Okay, how do you do gravitational wave spectroscopy? There's been a lot of work in this direction, in particular in Frankfurt. Let me explain it. So this is the time domain waveform, and this is the corresponding power spectral density. So this is the Fourier transform. The dotted line is the part of the inspiral, and so you have to imagine this goes up like a straight line. It's short because it's a short period we're looking at, and you can ignore it because what I'm concentrating on now is really the post-merger signal. So, you know, you have clearly 3 peaks, and this is what we saw, 3 peaks, and so we call them F1, F2, F3. If we had more peaks, we would have called them F4, F5, and so on. You have to ask yourself, what is producing this first peak? This is in a log scale, so this is the biggest peak by far, almost 1 order of magnitude larger. Well, you convince yourself this has to be this part of the signal, okay, from 5 milliseconds onwards, because there the signal is almost monochromatic at a given frequency, and so you would expect a very large peak over here. And then you can also deduce that F1 and F3, these 2 other peaks, are produced between 0 and 5, and these are sidebands of the frequency produced by this object. So what produces this signal is just that the hypermassive neutron is like a bar, and it's rotating, and because it's you know, as a net quadrupole moment variation, is emitting gravitational waves at twice the orbital, the spinning frequency, and this is what is produced over here. Okay, so this is a spectrum. You understand there are 3 peaks. This little point over here, this is the merger frequency. This is the frequency at which the 2 stars merge. How do you define this? Well, it's a definition. There is no peak associated with it. What you can do is, in general, the gravitational wave amplitude, if this is time and this is the gravitational wave amplitude, h plus modulus, will look something like so. We'll go up, and there's going to be a first peak, and then there's going to be peaks, and so on, okay? And we define the merger frequency at exactly this time over here. So this is merger. So it's the time when the signal has a first peak. In the case of black holes, you would have something like that, okay? After the merger, the amplitude goes down exponentially. Okay. This one you mean?
Yeah.
No. This is nothing to do with this. Okay, so you change equation of state. Now you have this other soft equation of state. The waveform changes completely, even in the spiral, because of tidal deformability, and of course in the post-merger. You look at the power spectral density, and you get the red one. And everything is different, but everything is also the same. You still can see an F2 peak, you still can see an F1 peak, you can still see an F3 peak, okay? So this is why, what I'm trying to explain is that although each equational state will have a different position of the lines, the lines are always there, okay? The same lines are always there. Now, look, the merger frequency has moved from 1 kilohertz to almost 2 kilohertz. Does anyone know why? The red one is a soft equational state. A soft equational state means what? The neutron stars are bigger or smaller? Smaller. So if they are smaller, they can get closer to each other, right, before breaking apart. And so the merger will happen at a higher frequency, and that's why it moves over here. So it's very simple. Now, all of this would not be useful if there weren't universal relations. And by that, I mean the possibility of relating one of these signatures with some properties of the star, independently of the equational state. The equational state we don't know. But if you say, if you imagine that what we do is exactly this. We take all of these dots, we put them, because we are computing all of them, we plot them versus some property of the star, say the love number. The love number has got nothing to do with feelings, as you probably know. Comes from a Scottish physicist who first considered this. What is a love number? Does anyone know? Wow. Do you have a love number? Yes, you do. It's not of your girlfriend. The telephone number of your girlfriend. Okay, so you take an object which is self-gravitating and is isolated, and is not rotating, it will be perfectly spherical, okay? Now you take the same very object into the gravitational field of another star, and it will no longer be spherically symmetric because there's going to be a tidal field. Part of this object will want to go towards the other one. This is called a tidal deformation. There's going to be a tidal field, and the ratio between how much you are distorted with respect to how much is a distorting field, so the ratio between the two quadrupole moments, is a love number, okay? So it's just a measure of how much you get stretched under a gravitational field if you have a given equation of state. And everything has a love number. I have a love number, you have a love number, probably very similar. But, you know, love numbers is, you know, tides are the consequence of the existence of a love number. So what you can do is you can take those frequencies and put them versus the love number of the different equation of state. And what you find, quite surprisingly, is that all of these frequencies are aligned or follow a certain functional behavior. In principle, these points with different colors at different equation of state could be all over the place, okay? But they are not. They follow a certain behavior, and this is what is called a universal behavior. Now, there is a bit of scattering, there are some outliers, but overall, there is this behavior. And this is important because this is, if you can measure this quantity, you know, it's just a measure you do of the gravitational wave, immediately you have a measure of the tidal deformability. And if you have a measure of the tidal deformability, you have a measure of the moment of inertia, quadrupole moment, or mass ratio, and so on. So this is the way gravitational wave spectroscopy can work. You measure something, and immediately through universal relation, you find out properties of the star. You can do this also with the other peaks. F1, for instance, can be related directly with the mass radius, the compactness. As you can see, it's a very tight correlation. And so once again, if you can measure F1, then you can measure immediately what is the compactness of the star, and you can measure what is the radius of the star, and therefore the equation of state. You can do this also for F2, the main peak. Again, you can see there is a quasi-universal behavior. Okay? So this is just a glimpse on a very active area of research that goes into looking at the post-merger signal to learn something about the equation of state. There have been a number of works that have worked out what is the precision at which you will learn, you can measure the radius if you see these peaks, okay? And we have worked on this, and we found out that if we are lucky with about 20 detections, we can measure the radius with a precision of less than 1 kilometer. Now, this is an interesting result, but also shows you how a theoretician is an incurable optimist. We haven't seen any of these signals, and yet I can tell you what happens if you observe 10 or 20. Why is it that we haven't seen any of these signals? When we've seen binary neutron star mergers, why is it that we haven't seen these peaks? Sorry?
So weak?
So weak, yes. They happen in a region, you know, they are over here. So they are below the sensitivity curve. The detectors are not sensitive enough at these frequencies. And so that's why GW170817, the binary neutron star merger, we actually didn't see the merger. It disappeared from the instruments because the signal went below the sensitivity of the instrument, okay? So that is why these post-merger signals are very exciting, although they are very hard to actually measure. Okay, what is it that we can, now, what is it that we can tell on the basis of this event, okay? So, what we know is that GW170817 was a hypermassive neutron star, and that's because the object produced had a total mass initially of 2.74, and this is way too big to be sustained by any equation of state that we know of. How can we use this number to set a maximum mass limit, limit on the maximum mass of neutron stars? Who knows what is the maximum mass of neutron stars?
1.4?
No, that's a typical. The maximum mass is the maximum mass that can be sustained. Okay. I see that most of you don't know this concept, although I don't believe it. But let me explain it. Suppose that you want to study equilibrium configuration of neutron stars. Okay, so you solve the Anson's equations in the form for spherically symmetric system. These are called TOV equations. Then you can build equilibria, and you can build a diagram of this type where you have mass on one axis and you have central density on the other, and you will produce a curve which has a local maximum. This maximum is the maximum mass for that equational state. In other words, if you put in more mass on this star, you will make it collapse to a black hole. Anything to the right of this curve is unstable, dynamically unstable. Note that I haven't put any numbers on this diagram. That's because this is a very logical diagram. It doesn't have, any equational state will have a different curve and different values. But you can find other solutions, and these are the uniformly rotating stars. These are shown over here. In principle, it should be green. It's certainly green on my screen. You don't see it. But between these two curves, there are all the solutions of stars that are uniformly rotating. As you can see, they can sustain more mass. And this line over here, the outermost, is called the Keplerian limit. This is the limit of all the stars that are uniformly rotating and at the maximum rotation speed. If you make them rotate a little bit more, you will break them apart. So this is the Keplerian limit. And you can see that also this limit has a maximum. And so this is the maximum mass that a star that is rotating uniformly can support. Anything larger than anything to the right of this M max is unstable and will collapse to a black hole. This line over here that joins these two maxima is called the stability line. It is, you can find it numerically or through some approximate criterion. But anyway, it's a line, and anything that crosses this line will produce a black hole. Now, why is it that we can tell what is the maximum mass? So my claim is that I can tell you, by looking at this number, I can tell you what is this number over here, independent of the equational state. The reason why I can do this is there is a universal relation that relates M max to M TOV. So independently of the equational state, once you know what is M TOV, you know that M max is 20% larger than M TOV, or vice versa. If you know M max, you know that by 20% less, you have M TOV. There are other solutions which are possible, and these are the differentially rotating stars. These are the stars over here. So any star which is above this limit, you can build, in fact, an hypermassive neutron star is in this area over here, okay? And you can show that the stability line also continues and goes up in this manner. Okay, so let's see. GW170817 produced an hypermassive neutron star, so at 2.74 solar masses, very high mass, and it then produces a gamma ray burst. And in the standard picture, a gamma ray burst needs a black hole. So that means that whatever produced GW170817 here must have gone across this line, because in order to produce a black hole, you have to cross this line. And so you have two options. Either you cross this line along trajectory number 2 or along trajectory number 1. And we think it was number 1 because number 2 would have happened way too fast, okay? This is the trajectory that I've shown you in the first movie. If you remember the first movie, the star was rotating, and the hypermassive neutron star was rotating, and then collapsed very rapidly in a matter of a few milliseconds. If you follow instead trajectory number 2, it takes much longer. You can take even up to 1 second or more, and that's because you are slowly losing angular momentum. Now, the reason why we exclude 2 is because there has been a very bright kilonova, which means that there's been a lot of matter ejected. And in order to lose all of that matter, you need time. You cannot immediately produce a black hole. And therefore, we believe that the trajectory that's followed is number 1. And this is written here because of the large ejected mass. Okay, so the picture we have is that the GW170817 has collapsed very close to M max, not exactly at M max, but very close to M max. So how do you put all of this information together? You know, we know what is the gravitational mass. We know how much mass has been lost because of the kilonova emission. We can use universal relation and account of all the errors and obtain the following estimates. Okay, so MTOV, the maximum mass of a non-rotating star, is between 2 solar masses and 2.16 solar masses plus a rather large error. This is an observational fact. We know that there exist stars with this mass, and so the maximum mass has to be larger, and this is what is coming from the considerations are made and the observation of GW170817. If you don't believe me, you think that all of my arguments are too vague, I just want to remark that in about 3 weeks, 4 different groups have published results, the same result essentially, using very different logics. Okay, so maybe I'm wrong, but all the others are right, and this still remains a good estimate. Okay, so now it's amazing how a single observation has already allowed us to set a constraint here. We can also use this to set some constraints on the radii, and this is shown over here. As I explained, we don't know what is the equation of state, but for a theorist, this is not necessarily an enormous problem. If you don't know what is the answer, maybe you can try all the possible answers. And so what we have done is we have parameterized our ignorance and written and built a very large number of equations of state. Okay, so in fact, we have built 1 million equations of state and 10 to the 9th on 1 billion stellar models. And in this way, we can start thinking of doing a probabilistic or a statistical approach to what is a typical radii of neutron stars. So let me just explain what we've done. This is a representation of an equation of state. You have pressure versus density, or number density. Here is normalized to the saturation. So this is the low density part. We use a BPS equation of state, which is pretty robust. Density here are very low, so we think we understand nuclear matter here. Then there is a part at very high density where whatever equation of state, it has to go to match the perturbative QCD calculations. And then there are other pieces over here between. So these two you can think are boundary conditions that you have to meet because we think we understand physics there. Then there is this part over here which can still be modeled with nuclear physics calculations. And then there is this part over here to the left to the right of this line where we can just say, well, try and have all possible piecewise polytopes that allow you to match this limit over here. Okay? So in this way, we build actually tens of millions of equations of state. Most of them we throw away because either they lead to maximum masses which are below 2, or they have sound speeds which are larger than 1. But at the end of the day, we have about 1 million equations of state that are good. So you have to stop thinking about diagrams of this type where you have a single line for a given equation of state. You have to think in terms of statistical distributions. So this is shown over here. So this is the probability distribution of this equation of state. This is the same diagram, m versus radius. And you can see that if you impose the very simplest bottom line constraints, that the tidal deformability has to be less than 800 and the mass has to be larger than 2, you have this distribution. So it's a rather large distribution. If you take a cut at 1.4, you go from 11 to 14 kilometers. But then you can start putting in new constraints, like for instance, the fact that there is an upper limit on the mass, or that there is a lower limit on the tidal deformability, or you can put all of the constraints together. And so you go from here to here. It may look not a big difference. Actually, it is a big difference because now you have restrained the range of possible radii. We can think of making a cut at 1.4 solar masses, and this is the distribution of radii that you obtain. don't concentrate too much on the various lines. These are different constraints. But what you can appreciate from the shaded region is that the radius distribution seems to favor radii between 12 and 13 and a half kilometers. In particular, the peak of the distribution is at about 12.5 kilometers. Okay, so this is an interesting and useful input, or well, output of the fact that we observed GW170817. We now have a better understanding of what are the typical radii. This means that radii as small as 8 or 9 kilometers seem very unlikely unless you have a phase transition, and equally radii which are very large, so very stiff equational state, seem to be excluded. So the equational state is kind of in between stiff and soft, which is maybe what one would expect. Because we have so many stellar models, we can also think about what is the distribution of the tidal deformability, and this is shown over here. So this is the log of the probability distribution function for pure hadronic equations of state. So this is lambda. Lambda tilde is related to the love number. And what you can see is that there are regions which are black, and then black means very low probability. So it's very unlikely to produce a star with, say, 1.4 solar masses and 200 tidal deformability. You need to have, for this mass, a much larger tidal deformability. So by just using this data, we can set a lower limit of 375 at 2 sigma, or a bit tighter at 2 sigma, for a 1.4 solar masses. Okay? So this is an example how the detection of gravitational waves can be used to say something about the properties of the equational state. The last part of my talk will be about phase transitions and their signatures. So we think that strangeness, or strange quarks, can appear in neutron stars. They could appear both in the spiral or after the merger. In particular, they could appear in the spiral in the form of hyperons. If the density is sufficiently high, then matter, as compressed, will produce hyperons. But certainly they will produce after the merger, because the density there becomes much larger, because matter is squeezed. Now, isolated neutron stars probe a small fraction of the phase diagram. Okay, this is a phase diagram. How many of you know how to read this phase diagram? Oh, okay. So no one of you is a nuclear physicist. Well, nuclear physicists or particle physicists like to think in terms of phase diagram, where diagram where you have temperature and density, or chemical potential. And early universe is very low density, very high temperature. Neutron stars are over here, very low temperature, very high chemical potential. And this is the region where a phase transition was expected in the past. Effectively, there is a crossover. And these are the regions which can be either tested through lattice QCD calculations, or low energy heavy ion collisions. And as you can see, neutron star mergers can also cover a part of this phase diagram. So we can probe what happens to matter when you go at temperatures of the order 50 to 100 MeV and density over the few thousand MeV. So the idea has been of checking whether or not the collision of two neutron stars can lead to a phase transition and the production of strange quark matter. What we've done is we consider an equational state which is based on CMF and a nonlinear SU3 sigma model. This includes hyperons and quarks, and these hyperons and quarks can be either switched on or off at our will. And we use a Polyakov loop to implement a strong first order transition. And at a high temperature, we use a crossover so that we can reproduce the prediction coming from lattice QCD that there should be a crossover. Okay, so in this way, we have built essentially an equational state of two equational states which are identical at small density or masses, and then can differ at sufficiently high density, leading to this other branch over here in the pressure. So what I will show you now is the result of a simulation where we have used this equational state. And this is a complicated plot, so I will guide you through it. What we have here is temperature with this color code, so black to white through red. And I also show you the quark fraction, again, black to white through purple. Here I'm showing you two sections, one on the meridional plane and one on the equatorial plane, okay? So again, temperature on this side, quark fraction on this other side. What you can see is that there where the temperature is very high, also the quark fraction is very high. The upper mass neutron star at one point reaches temperatures and density sufficiently high that a phase transition takes place. You will see here the quark fraction becomes very, very high. At that point, the equational state softens enormously. There is a lack of pressure support, and the star is doomed to collapse very rapidly. You can see this better maybe in these snapshots. So what you can see is that there where there is a high temperature, there is also high quark fraction, high temperature, high quark fraction, and this is very close to the collapse. There is a large quark fraction in the core. This takes away pressure, and you are doomed to collapse to a black hole. Because we can play with the quarks, switching them on and off, we can really see that the only difference in the dynamics is in the quark fraction. You see that, so this is snapshots with quarks, this is with a full hadronic equational state. So obviously everything is black here, while here there is color. But if you look at the temperature distribution, it's pretty much the same, which shows that, you know, this is really a very fair and a robust way of asserting the presence of quarks, because we have essentially the same configuration, and the only change we make is by switching quark presence or not. This is again the phase diagram, and this is an even more complicated diagram to illustrate, but this is something that our particle physics colleagues love, and so we decided to produce such a diagram. What you see here, again, with this color code is the quark fraction. So no quarks here, lots of quarks over here. And this is a crossover transition. And here this is a first order phase transition that in terms of the number density is spread, is not a single line, but is spread over a certain range. Because we control everything in the simulations, I can calculate what is the temperature everywhere. In particular, I can calculate what is the maximum temperature after the merger, and I can show the evolution of the maximum temperature as a function of time. So this is shown over here. You see just circles, and the colors in the circles shows the time evolution. So this is brown is about 6 milliseconds after the merger, and then the star remains here for some time, for quite some time, and then goes off to become very large and then crosses this phase transition region. I can do the same for the density, and I can track the position of the maximum density as a function of time. And here the color code is white to dark green. So you start over here, and then you go over here. So just to make it clear, at the beginning, 6 milliseconds after the merger, you have temperatures in this range, densities in this range, and temperatures in this range. Then the temperature and the density, both of them grow. They transit this region of the first order transition, and then they produce a full phase transition. How does this? Well, so let me just a final remark on this. This is the first time that we've tried to put in together two different communities. Particle physicists think in terms of phase diagrams. We, gravitational wave physicists, think in terms of density and temperature and gravitational waveforms. And we can have both of these quantities in the same diagram for all to benefit. If you ask yourself, how does the gravitational waveform look like? Well, this is shown over here. So the black is a fully hadronic equational state. And the red is the one with quarks. Also shown is the frequency evolution of the signal in red or in black. And in blue is the phase difference between the two signals. Okay? As you can see, the phase difference is at 0, essentially up to 5 milliseconds after the merger. This is because essentially there are no quarks or very little amounts of quarks up until this time, but then as soon as quarks appear, they lead to a difference in the phase. You see the waveforms are different, and this phase difference can be quite considerable. You can also see that when the phase transition is very strong, all of a sudden there is a collapse to a black hole. Okay? While in the absence of quarks, the black hole collapse would happen later on. So this is the way you could tell, in principle, that there was a phase transition. You look at the inspiral, and you're convinced that this is a perfectly hadronic equation of state. There is no appearance of hyperons or quarks, and everything matches what you would expect for an hadronic equation of state. Which also means that you know that the collapse would happen at a given time. And so if the collapse happens earlier, that is a strong signature that there was a phase transition. Okay? So it's a mismatch between what you see in the inspiral and what you actually see after the merger. That would be a signature. This is for a 2.8 solar mass neutron star. If you have, this is already said. If you have a slightly larger mass, 2.9, the difference becomes even more subtle, but they are still there. The phase difference is limited to a very small amount of time. The difference in collapse time is very small, a few milliseconds only, and so might be harder to detect. However, the ring down signal is different in the two cases. So even if you are close to a situation like so, chances are that you'll be able to tell the difference by looking at what you expect from the inspiral and what you observe from the post-merger. So this is what I've just said. A mismatch is a signature of a phase transition. There are other ways in which you can measure this phase transition by looking at the frequency of this part of the signal over here. And suggestions are that for some equations of state, this frequency doesn't match the expected behavior that you would see. In our case, this is, as you see, this is not really the case. The frequencies are really the same. Okay, let me do a recap of what we've seen for the first lecture. I think I've explained that the spectra of post-mergers shows quasi-universal peaks, and that you can do gravitational wave spectroscopy by looking at the post-merger signal. The signal-to-noise ratio for these peaks is very small, but if you have multiple signals, you can stack all of the signal, and the signal-to-noise ratio will increase coherently. So that if you have about 20 detections, you can set constraints of about 1 kilometer on the radius. In the case of GW170817, we just seen the inspiral. We haven't seen the post-merger, unfortunately. But already with that, we have learned quite a lot. In particular, we learned that there is a maximum mass. There is an upper limit on the maximum mass, which is 2.16. And we set new limits on the typical radii and tidal deformabilities, which is the ones over here. Finally, I've shown you that phase transition can take place after the merger, and they lead to a clear signature. Okay, thank you. Questions? Yes.
Is there any way to produce a short gamma ray burst by a stable neutron star or a long-lived neutron star?
A stable neutron star?
Or a long-lived neutron star?
Well, so there are people who suggest that effectively this is what happens when you see what is called an extended emission, a short gamma ray burst where the emission in the X-ray lasts for very long times, of order of 100 seconds or more. Okay, it's very hard to explain this emission in terms of gamma ray bursts with an accreting torus, because the torus will be accreted in the order of a few seconds. So how do you produce an extended emission. So how do you pump energy into the system, into the gamma ray signal, into the X-ray signal, sorry, for such a long time? And the idea is that, okay, there is a merger. This merger doesn't lead to a black hole, but leads to a neutron star, a protomagnetar, a star which has a large magnetic field, which is losing energy through dipolar emission, and in this way it can energize the emission, the X-ray emission. There are at least two problems with this picture. The first one is that if it is a star that is producing the extended emission, what is producing the gamma ray emission? Gamma ray emission is normally thought to come from inner shocks in an ultra-relativistic jet. And short gamma ray bursts have evidence of the production of jets. If you have a protomagnetar, it's impossible to produce a jet. At least we don't see any evidence of jet formation as long as you have a star. So there is this mismatch between how do you produce a jet. The second difficult thing to explain is the extended emission comes after the gamma. You first see the gamma and then you see the X-ray. It is possible that you produce a long-lived neutron star, but this then has to collapse to a black hole. And so you would expect that the signals arrive in the other order. You first see the X, and then you see the gamma. There are ways out of this, I have proposed one of these way outs. Okay? But it is possible, people are invoking it, and I think it's a good explanation, a potentially good explanation to explain short gamma ray bursts which have a very long X-ray emission.
For neutron star black hole mergers, do we also expect similar spectral lines?
No, unfortunately not. You see, if you have a black hole neutron star system, you can either be very unlucky or not lucky. The lucky is not an option. This is because, in general, if the mass ratios are realistic, you would expect that neutron star is accreted without being disrupted. And in the not less unlucky situation, what is going to happen is the neutron star is broken and produces a torus. And so it doesn't have, you don't have a metastable object which is emitting gravitational waves at very large amplitudes. So you will not see a spectrum as in the case of binary neutron stars. You would see a cutoff also in that case. Yes?
Why gravitational wave frequency is decreasing in transit region and increasing afterwards? The transit region in neutron star merger, but not in black hole wave.
I'm not sure I understand fully your question. So let me bring up. I think you are referring to this slide, or
no,
to this one.
Yes.
Okay.
The transition in.
So the frequency here is not much different from the frequency here.
Frequency in the transit region isn't being lower compared to.
So the transient region here, it will. Yes. So this is the waveform. Okay. Suppose you do a cut. And you just look at the signal after 5 milliseconds, what you would see is just F2. You would not see F1 and F3. And suppose now you do a cut between 0 and 5, what you would see is F1 and F3 and a very little F2. So this means that these two peaks, F1 and F3, are really produced over this period of time between 0 and 5. And to explain how this works, imagine the following mechanical configuration. You have two objects which are connected, two spheres, with massive spheres, which are connected with a spring, and they are also rotating on top of a disk. Then what is going to happen is that you can allow, the disk is rotating at a given frequency omega, and the two objects will oscillate at another frequency, let's say little omega. What you can imagine is that the moment of inertia of the system will change in time. That's just because when the two spheres will get closer to each other, the moment of inertia will go down. You know, moment of inertia goes like mr squared, r is small, and so I goes down. The angular momentum, which is I omega, because we'll have to be conserved, and so if I goes down, omega is to go up. So in this system, as the two spheres go and get closer, the system itself will slow down, and vice versa. When the two stars move, when the two spheres move apart, it will go up. So the actual evolution of the angular frequency of the system will go between up and down, high frequency and low frequency. So there's going to be a omega, say 1 frequency, and omega 2 and omega 3 frequency. This is when the two stars are, you know, the highest frequency, when they are when they are closer to each other. Okay, it's a bit like a ballerina. Now, why is it I'm doing this toy model? Because this is exactly what happens. The two stars at the beginning are essentially two stellar cores which are merging. They compress each other and then they bounce, and at the same time they are rotating. And so they do this. And while they do this, they produce this sideband signal F1 and F3. Okay? So this is F1. So this is F3, the high frequency. This is F1. Is it clear?
I don't get the part why gravitational wave signal that dumps just afterwards.
Because, you know, the two stars there is a constant in the spring, but then is also dissipation. And so at one point the two stars stop bouncing and they just move at the same frequency F2. Okay? Try to picture this in your mind. Yes?
Can you modify the mathematical formula, the mathematical structure you described yesterday in order to simulate the equation of state and extra properties such as temperature, stiffness, or
No. The equations really don't know anything about that.
everything in T mu?
Everything is in T mu nu, and it just, well, it is more complicated to handle the equations because they have become more delicate. But, you know, at the end of the day, there is a routine that says, give me the pressure if I tell you what is the density and temperature. Yes?
If one of the components or both of them are white dwarfs, then shall we see such lines, and will you see?
So if there are white dwarfs, they would also produce gravitational waves. White dwarfs, though, produce gravitational waves at much lower frequencies. And these are frequencies that will be detected by detectors like LISA, not LIGO. When two white dwarfs merge, they are also producing some interesting firework, and they may lead to a supernova. More questions? Okay.